So it's been a while. Well, actually a while, 5 days. Where did we leave off? Does anyone recall? We finished lab 2, and now, so we're into lab 3. So let's take a look at lab 3. All right, practice with mathematical expressions. So I'm going to go through this and do it, and then we'll talk about, the topics that are covered in your reading as we go through this exercise together. And then when you go into lab, whether it's lab here on campus or lab at home on your personal computer, that you'll be able to repeat and review the concepts. And please make sure that you do the reading so that you're understanding the concepts as you're carrying out the exercises. So we have 2 labs done already. If I do ls minus a, I see, oh, there's that .svn folder in there. That's a hidden folder. Remember, when you're working in the labs, don't copy whole folders to create new labs, because you're going to end up copying the .svn folder within it that you don't see, and that will interfere with the operation of subversion. So please keep that in mind. See, all of these lab folders have that subdirectory, .svn subdirectory in it with information about it. So if you copy a folder, you're going to copy that subdirectory, and it's going to create a conflict when you try to operate on the repository. All right, let's go ahead and do this lab. I'm going to do this as if I were you, so you're going to see pretty much exactly how to carry out the lab. So here's the first exercise, and let's go ahead and add that to the repository, and then let's go into that lab. And maybe we'll copy a main.cpp file from an earlier lab so that we don't have to bother doing that again. Here's that triangle program. We'll just say OK. So we compile the program, then run it. See, this is what I do. So you should get set up. Remember, you want to solve things incrementally. And before you proceed on to the next step, make sure that what you've done already makes sense and that your build environment is set up. You've got your folder set up correctly. You can compile or run a simple program. So now we're ready to proceed. Okay, write a console program that prompts the user for 3 double precision floating point values, x, y, and z. And then have the program compute and display these things. All right, so let's go ahead and do that. Prompting the user. So in other words, something like this. So we would say something like x equals, and then we'll read in x. That's it. That's how you prompt the user and read in the value. So here we have the standard output stream, and then we have a string that's enclosed in quotes, and we send that string to the standard output stream using the output operator. That's the syntax for doing that right here. The whole statement is terminated with a semicolon. So I didn't use /n in here, so we're staying on the same line in the console window. So the system will print x space equals space, and then it'll wait right there. The user will type in a number, we'll read that number in. In order to read that number in, we need to declare it. So here we're telling the compiler that I want a variable called x, which is of type double. Please create the storage for that now. And then wherever you see the letter x from this point on, have it refer to that storage location that was allocated.
Now, what was the difference between double and float?
A double is 8 bytes. It's an 8-byte representation of a floating point number, and a float is 4 bytes. So if you have a lot of data and you don't need 8 bytes of precision, you can go with 4 bytes, and you're going to save half the storage space. Let's go ahead and run that. Oops. So there it is, x equals. It's waiting for an input, say 12.3. One thing that we're not going to do, let's suppose we put in like s. It says OK. But it's actually not OK. But I'm not going to get into that right now. That is, that this operation has in fact failed. Actually, let's get into it a little bit. Let's initialize x to a known value. Make it easier to see what's going on. And actually that's maybe I should go into it a little bit, but it's not really required in the labs to do this. There's something like the input stream is now in a failed state. And I think it looks something like this. Let's just do some investigation. I think there's a function called fail here that checks whether the stream is in a failed state or not. There it is, says C in failed. But if I put in a good number like 3, it doesn't print it. So some of you might end up, if you take later courses and computer science courses, you're going to need to know how to do this stuff. But in this course, you don't need to. I don't think now. I just have to. At this point, I don't think we're going to need to check the failed state of the input stream. All right, well let's I'll talk about it a little bit more, but it's kind of an optional topic. Just take that out. And actually, we'll just leave it in there. Why not? All right, so read in the x. Let's go ahead and read in y and z as well. So it's pretty much the same thing.
If you already predetermined that x is going to be equal to 0, how come you're still able to put in that x is equal to 0 stream?
But see, that's why they call it a variable. X is a variable. Its state varies. Its value, the value that it represents in its storage, can change. So we initialize it to 0 here. So that's its initial state. When we create, the compiler generates machine instructions that allocate storage to store this double, 8 bytes, and then it initializes it to 0. Here, the bytes that are in there, the bits that are in those 8 bytes are then modified based on this operation. So that's why they call it a variable. Its value varies. All right. So let's just get all of these. So X, Y, and Z. I guess we can test that. Let's test that. Remember to build X and Y and Z. So, looks all right. All right, let's compute these things. The sum of X, Y, and Z. I'm just going to paste that in there. Whoops, that didn't work. There we go. And let's do it like this. So we're using this cascading form of the output operator. Should it be what? Oh, yeah, that's right. Thank you. So you need to mentally parse this. Here's the first use of this operator, the second use, and the third use here. So it's 3 operations. This is the first sub-expression that's evaluated. So the evaluation is left to right. So the leftmost output operator runs first. And this whole sub-expression evaluates to Cout itself. So after it completes, you can think of it as being replaced by Cout. And that means Cout becomes the argument for the next output operator. But that operator doesn't run yet because this sub-expression needs to be evaluated first. In fact, that has higher precedence. And once again, this is also left to right. So the first X and Y are added together. After that sum is computed, the result is then added to Z. So it's left to right evaluation.
Will the computer take into account order of operation?
It does. It does. It takes into account. It's the compiler, actually. The compiler generates machine instructions. The compiler will generate the right machine instructions to take into account the order of operation. So the compiler will we don't know exactly what it's going to do, but it will generate the machine instructions needed to add these two together and compute a result before the machine instructions needed to add Z to the result. So it's not the computer that does it, right? It's the compiler that does it. And then the computer just executes those machine instructions that the compiler generated. What is going on here? Let's take a look at that. So if it's 2, 2, 2, she gets 6. There it is. All right, let's, we have something similar. The next, whoops, wrong key. What is the sine of x? So this expression needs to be done differently. So it'll be the sine of x it's a mathematical function, and this compilation should fail. Let's see it fail. Error. Sine, the a hat, those should be quotes. Sine was not declared in this scope, so the compiler's complaining that I don't know what sine means, right? So we have to tell it to look in the in a header file that has a information about that function. And that header file is called cmath. I think it's cmath. The IO stream, that's the header file that has information about cin and cout and those output input operators. Now it works. X is 1, Y is 1, Z is 1. The sine of 3, I'm sorry, sine of X, sine of 1 is 0.8. Is that right? What's the sine of 0? 0, right? Let's try that. Whoops. Look at that. I put in an O. All right. So we have code in there to catch us that. So sine of X should be 0. There it is. Okay. Now we could try the other things. I think it takes radians and not degrees. We could check that as well. Right? So let's wait on that. Okay. Yeah, the argument to this sign is in fact radians. Let's check. Let's prove that to ourselves. Let's prove that it's not degrees anyway. That's the easy one to do. The sine of 90 degrees is 1, right? Okay, so if I type in 90, I shouldn't get a 1. If it's if the sine takes degrees, we'll get a 1. If the sine takes radians, we'll get something other than a 1. So we have something other than a 1. That looks suspiciously similar to 0 here. Oh no, not 0. Was it 1? No, they're not the same, are they? They're different. Okay. All right, so it takes radians. Let's look at the other functions. The cosine of x plus y divided by z. The cosine of x plus y divided by z. Does that look right? It doesn't look right to me. Because the order of operations, division has higher precedence than addition. Oh, I didn't say, did I, in the web page? The cosine of x plus y divided by z. So actually this is ambiguous, isn't it? Let's fix that. How should I make that non-ambiguous?
Run the x and the y if you want.
The cosine of, like this?
Yeah. You want it to happen before the division.
And put a comma there even?
Cosine divided by, you want x, that's y.
Oh my gosh.
That's the cosine. Cosine of
You know what? You can't do it in English. It doesn't work. We got to use math here.
Would you have to do anything so that the computer would take a value in the denominator of 0?
Yeah, that's right. We'll get a failure if we try to divide by 0. Let's go ahead and do that, okay? Let's see what happens when we divide by 0. How about that?
Yeah, that's good.
That'll do it, right? And then you put it in italics there. That's what I was thinking anyway. So now we use a little math there. All right, so well, we kind of gave away the answer there, didn't we? We just pretty much we used the same syntax that we would use in writing down the math equation. So what happens if we pass in 0 for z? If we're going to end up dividing by 0, it's going to who knows what happens. Then we're going to take cosine of the result, right? So should fail. There's no automatic checking for us, so we're going to get some kind of random behavior. Because there's no checking in C++. You might find that something is checked in another language when you divide by 0. It's set to, like in JavaScript, I believe you divide by 0, it's set to nan, N-A-N, not a number. So let's go ahead and try this. 1, 1, and z will be 0. Oh, I didn't compile it. Thanks. Did I save it? And I have the line in there. Let me make sure I saved it. Compile. Run it. 1, 1, and 0. Oh, it's a nan. Not a number. N-A-N. So that's it. But in a program, you would normally check. You would want to condition this calculation on z not being 0. So you check to see if z was 0, or if z were very, very close to 0. That would be a problem too, because then the number is going to be too big, and the number might exceed the capacity of the machine to represent the result.
So can you prompt the user for a number other than 0 for z?
So you would require that z be non-zero before even running this line. Did I answer that or not?
Well, no, I was saying because you're asking for values
Yes.
x, y, and z, but you're not telling the user.
Oh, yeah. Oh, right. That's right. Thank you. So we could say, let's do it like this. No, we'll do it like that. Like this? Something like that, right? It's not very good. Oh, do not, so not. Yeah, we could say something like that. Just gives the user some information. Actually, that's not very good. But if you saw this, watch this. what are you going to want to do?
Enter 0.
You're going to want to put a 0 in there. Exactly. So it's, we really need to check. We need to check on that, right? So also we want to put a we're not at this point yet, but this is called an if statement, right? So if z is 0, we can scold the user. Yeah. You have to use 2 equal signs. And the reason is that that's what's required for comparison. It says you're bad. Okay. Yeah, this is a comparison. So a single equal sign is assignment. 2 equal signs is comparison. So this, in fact, this will overwrite the value that the user entered and set it to 0. So we will always get not a number. So I put in good numbers, I'll still get nan because we have a bug in our code. We're doing assignment here. We're signing 0 into C, and then we end up dividing by Z. We need to do a comparison. Compare Z with 0. And the result, this expression here evaluates to true or false. It's called a Boolean expression. It has 2 states, true or false. And here, and that becomes an argument to this if statement. So these if statements take Boolean expressions that evaluate to true or false. I'll do what's in my block here, my code block. I'll do what's between my braces. I'll do this if that expression evaluates to true. So if z equals 0, if this evaluates to true, then I will print this. Question?
How do you get it to, if they enter 0 for z,
Yeah.
how do you get it to just loop back where they have to enter it?
Well, then you need a loop. So we have to, in other words, they could just keep entering 0 over and over again, right, until they get tired. Then they'll put something else in there. So you don't know how many times you need to present the prompt. You don't know if it's 5 or 50, or whatever. So you need a looping mechanism. So to be able to, you need code that will repeat the prompt and the reading of the value over and over again until you get a non-zero value. Well, maybe we want to, that's the top, that's not the top. I don't want to jump too far. That is the topic of the next reading assignment, I believe. So we're in reading 3, which is, so reading 3. How to write loops, yeah. So this is reading 3. Let's do that. I mean, that's good to do it right away, actually. No, we're in lab 3, is that it? Yeah, okay. So then we have to do this unit conversion and then this web page. And let me wait on that because we still have to do a lot more here first. I don't want to run out of time. So that's basically how to do the do these problems. Now let's go ahead and use SVN and add our work to the repository. So we're just going to add in main. We're not going to add in that a.out. In fact, we could delete it. RM for remove. There's no reason to have that hanging around. And You can see I'm in my CSE201 folder. Now let's do a commit. And that got that got uploaded. And if anybody here is having trouble with that, please see me after lecture to get that fixed. It's not hard to get that working right, but usually people have trouble. So it takes a little while to get it going. All right, let's check our work in the web server. So it should be here. There it is. There it is. Okay, good. So we verified that that was uploaded. All right, let's take a look at this unit conversion. Exercise 2. Remember, don't copy a folder. You can copy files. You can copy main.cpp, but don't copy the whole folder. You're going to end up copying the .svn control subdirectory, and then the subversion will not work at that point. So as you can see, I am making a fresh folder. I'm not copying a folder. Now I'm going to do the copy. Oops. All right, that's okay. Where did I copy that from? Oh, I see. I got it from there. All right. All right, unit conversion. Write a console program that converts meters into feet and inches. The program starts by asking the user for a measurement in meters. The program should accept a floating point number. After getting the number, the program computes the number of feet and inches equal to the specified number of meters. The program outputs feet and inches as whole numbers. The program should round the number of inches correctly. Test that your program produces the following outputs for the given input. So the program is going to prompt the user, please enter a number of meters. The user is going to enter that value in. It's a floating point number, has a decimal point in it. And then if the user were to enter this in there, we should get this as a result. Right? The number of feet, the number of inches, rounded to whole numbers. So let's start by reading in the value. So it's a floating point number. And it sounds like you want to create a float. And you can. It's all right for the lab. But in general, we're not creating a lot of these numbers. So the rule of thumb is to use a double. Let's read the value in. And that's it. Do you have to include what?
Anything else at the very top for the conversion? Instead of iostream or CMAP?
I'm not sure yet. Maybe not. Probably not. I don't think so. We don't need to use like sine or cosine. We don't use that. We're just doing, using basic mathematical operations, which are part of the base definition of the language and not a part of the library. The library gives you extra functionality, right? The C++ library gives you sine and cosine, gives you those additional math functions and other things as well, right? So let's go ahead and go in there. How many meters? So we're reading in the values. These are the inputs we want to test, by the way. We could test more too. That's good. So we read in the value, and now we want to generate the output. So it'll be something feet, something inches. So it'll be something feet. Now let's do it like this. The feet will be an integer. Just set it to 0. And the inches will be an integer as well. Set that to 0. And so we're going to output the number of feet. Let's put in some funny numbers here. I'll put in 3 feet and 11 inches. So it'll be first we output the number of feet. Now that's a variable. So we set it to 3. But that's just for testing right now. And so we want a space. And then do we want a space there? Is that how I show it? 1 space ft space 0 space in, like that. Right, that's the whole line. I don't think we need this OK. Get rid of that. Let's see if that works. How many meters? 2. 3 feet 11 inches. Okay, so that's how the program should look. Right? Now let's go ahead and do the calculations. So the feet, how do you convert meters to feet? So we need to know how many, if we have meters, we want to divide by meters per foot, right? Or divide by feet per meter. How do we convert from meters to feet? Divide?
Yeah, because you're starting with meters and
Yeah.
you're dividing it into feet.
All right, so we're going to divide by feet per meters.
No, you divide by feet.
Oh. Divide by feet?
Yeah, because you're outputting feet, so it'd be.
All right, if I have 1.2 meters.
1 meter equals 3.280.
All right, so let's do it like this. Double, this is meters per foot. Is that what you have? Or you have feet per meters, right?
Yeah, but what I'm saying is that there's more feet in 1 meter than there are 1 meter in a foot. So you want to divide the meters into feet, like into equal spaces long that are going to be feet. So we have meters divided by feet.
So there's approximately 3 feet in a meter. So it's going to look something like, like that. Okay? It's about 3 feet in a meter. So if I got, is that right?
3.3.
No, it's the other way. A meter is big.
A meter is equal to 3.3 feet.
Yeah, so this This should look something like this. That's how many, that's feet per meters. It's just 3.1 feet per meters, and I want to do that. What do you have there?
3.3.
3.3?
It's actually 3.2808, but round to
3, no, I don't want to round it. 3 point what? Give me all the
28083.
280839. Did I get it?
Yeah.
One more 9? Like that? 2808399.
Yes.
Okay. So that is feet per meter. That's your feet per meter. So if I have 1 meter, then I've got 3.28 feet. So we're going to end up multiplying. Does that look right?
Yes.
Now this is a double, and this is a double, and we're storing the result in an int. So what happens when you take a double and you store it into an int? It truncates. So any values to the right of the decimal point are discarded. If the result of this is 1.9, then feet equals 1. And we toss out the 0.9. We're not rounding. We're truncating. We'll let this at 0 for now. How many meters? So 1 meter. 1 meter is 3 feet. That's right, isn't it? 1 meter is 3 feet. Now, I want to explain this a little bit more here. Just to prove a point. I'm going to ignore the calculation. I'm just going to store 1.9 in feet. Then we're going to print feet down here. What gets printed? No. A human calculates 2 because a human rounds up. But here the computer truncates. It tosses out the 0.9 and it only prints a 1. See, there's the 1. It doesn't round it to 2. There's a simple way to round, by the way. And whatever the number is, you just add 0.5. That's how you round up. So if you're at 0.6, then adding 0.5 is going to put you past to the next integer. If you're at 0.4, adding 0.5 is going to bring you to 0.9. You're still going to get truncated off. You're not going to go to the next integer. So rounding is a very simple operation. You simply add 0.5 before. Add 0.5 to your floating point number before you try to store into an int, which then does the truncation. Now what do we do? How do we get the inches? Well, the inches how are we going to figure out the number of inches? So let's think about that. We have to take out, this is the number that we have right now. We've got meters. And we're going to remove, I see this is meters. How about if we do this? We're going to do total inches. We'll take the number of meters times the feet per meter. That gives us total feet. Let me do it like this. We'll break it down. This is our total feet, right? And then the total inches is the total feet times 12. So if we start with meters and we multiply by feet per meter, we're going to get total feet with a decimal point. And then when we multiply by 12, we're going to get total inches. Total feet times 12 gives us our total inches. But this, this total feet here, now we're trying to compute inches. The inches it's kind of like the inches are like a remainder. We don't want the total inches. We want to take out the feet that we've computed up here. So we take out, that's it, we do it right there. This is the total feet. This is the feet to be converted to inches. Let's do it like this. Feet to convert to inches. How many feet do we need to convert to inches? This here, that with the truncation, this gives us the number of feet, the whole number of feet that we can pull out of the number of meters the user entered in. And now we repeat that calculation here because, see, when we did this, when we assigned it to feet, we truncated. So we made the number smaller. So we're doing the calculation again. Now we get the bigger number, the one that has a decimal value in it. But we have to take off the feet. And that gives us the fractional number of feet that we still need to convert to inches. So this number is always less than 1. And I'm going to show that with an assertion here. That this number is less than or equal to, it should be less than 1. So we're going to be using, the book covers this assertions, I think, in the next chapter. We're going to use it a little early here. Say it one more time.
Because you changed up above where it says double feet to convert to inches, you changed that to that from total feet. So don't we have to change total feet?
Oh yeah, that's right. That's right. Whoops. Let me do that. So this line down here, right?
Yeah.
Thank you. So that gives us total inches. This is total inches as a double. Well, why don't we just simplify it here, make this an int. And we'll do the truncation. But the Exactly. Thank you. Very good. So we want to add the 0.5. We want to round up. This assertion, what this statement does here is if this expression evaluates to true or false, okay? And if that expression evaluates to false, the program will crash with the failed assertion message. But if that expression evaluates to true, then nothing happens in this statement. It just quietly moves on to the next statement. So we can use these assertions to check our logic. And our logic at this point is that we want to know, here we compute the number of feet that we're going to print. And when we do this calculation, you know, we take the meters, so we multiply by feet per meter, and it gives us some number with a fractional part. We toss out the fractional part, we truncate, and we just get our feet. But now what we want to do is we want to get the fractional part. We need the fractional part because we're going to use the fractional part to calculate how many inches there are. So we recompute that expression again, and then we subtract out the number of whole feet that we're going to display to the user. And that should give us that fractional part that in units of feet. So the feet should be something like 0.2 or 0.9, whatever. It's going to be less than 1. So let's make sure our logic is correct. We'll just throw in an assertion here. That number will always be less than 1. You'll be surprised at how often your assertions fail, by the way. And that's one of the reasons to use them. Because when you write programs, your reasoning is always, not always, it's usually approximate as you're going through the problem-solving process. And you're going to get more and more precision and focus in, zero in on a solution. And as you're going along, you're going to say, well, you're going to be making mental assumptions about things. And it's a good habit to express those assumptions with assertions in your code. All right, let's go ahead and run that. How many meters? You know, let's go over here. This is these are the numbers, right? Let's try 1. 1 should be 3 feet 3 inches. There it is, 3 feet 3 inches. And 2, 6 feet 7 inches. 6 feet 7 inches. All right, let's put this one in there, 0.3049. 1 foot 0 inches. So those, actually, in the last quarter, we developed those test cases. And the reason for those particular numbers is that they will check to see if you're failing to round the inches at the end and some other things. So those are specially picked test cases. Here, I believe there's a rounding up. Here, there is no rounding. It's just no rounding on the inches. And this one, I can't remember. This is something useful. All right, that's it for exercise 2. Let's commit that to the repository. I'm going to delete that a.out file before I do svn add. I did that because there's some trouble committing those binary executables that get generated. So I want to make sure I delete it. We had some trouble last quarter with that. You don't always have trouble, but it's safer just to remove the a.out. It's a derived file. It's not supposed to be in the repository anyway. You should only put source files in the repository. So now if I add the whole folder, it'll add the folder itself plus the contents. And if I didn't delete the a.out, it would have added the a.out. It's not a big deal. We can remove it, but it could trigger a failure when we try to commit. svn commit. Done. There we go. So we've completed that exercise. There it is. So, you should keep in mind about the truncation and the rounding. It's not only true in this C++ language, but in practically every other computer language, it's the same deal. You've got truncation when you convert from a floating point value to an integer value. And to do rounding, you simply add 0.5. Also, the math expressions are very similar, identical. All right, here's the next exercise. When is this due, by the way? Is it Lab 3? Are we ahead of the schedule? February 1? And so we've got some time, right, before that's due. We could do this now, 10 minutes. We could fly through this. Or do you want to wait and do it next time more slowly?
Can you go back and show us the loop for the...
Oh, the loop. Yeah, we can do the loop. Let's do the loop. I'll show that to you quickly. And those who don't want to, just to get you some initial exposure to looping, because we're going to do that probably in the next lecture anyway. So we'll just take a quick glance at looping, and then we'll finish. So let's go into Lab 3. Was it number 1? This one here. Okay, so here, we ask the user, don't enter a 0. And they're going to enter a 0. So we're going to loop while z is 0. Get rid of that space. While z is 0, we're going to prompt the user for z. We're going to read it in. We'll put, but let's do it like this. I'll comment this out. We put this in later, just to give you the basic idea. So we set z to 0. So we know z is initially 0. And we say, do not enter 0 for z in the following. And then we have this condition, while z equals 0. And we know that's true because we initialize z to 0. So this is true. So it's going to execute the loop. As long as the loop condition is true, the body of the loop, that is the statements that are enclosed in the braces, the body of the loop will execute repeatedly until the loop condition becomes false. So while this is true, if the user keeps entering in a 0, we won't terminate the loop. We'll keep repeating. So this is how the loop works. When the system hits this point, it says, "Wow, oh, I've got a loop. Let me calculate the loop condition. What's z? Z is 0. Compare it to 0. 0 equals 0. That's true. Okay, let's execute the loop." Then it does this. Does the c out. Then it does this. It reads the z. Then it hits the bottom of the loop. And it says, "Oh, I hit the bottom of the loop. I got to go back and start all over again. Let me check the loop condition." If the user typed in a 0 again, or for the first time, if the user typed in a 0, the loop condition will continue to be true. So we will do the statements in the loop again. Once again, we hit the bottom. Let's suppose the user enters a 1 this time. When we hit the bottom of the loop, we'll return back up to the top and we'll check the loop condition. The loop condition is now false because z is 1. If the loop condition is false, that means we hop over the body of the loop and we continue execution at the next statement, which is down here. Does everybody know what these are here? These 2 slashes? Comments, yeah, right, so there. So x is 1, y is 1, and then we just 0. When we put in a 1, it takes it. So that's how to use a loop in that condition, that situation. You can't do anything without loops. No, loops are so important. And it's always a race to get to loops when I teach this class, because you can't really do anything practically without loops, and also conditionals like if statements. Those two things give you the power that let you do a lot more. All right, that's it. For those who have trouble using Subversion, please see me right now. Okay, I want to get that fixed.